So if we have a balloon that has a volume of 3.7 liters at a pressure of 1.1 atmospheres and a temperature of 30 degrees C, if the balloon is submerged in water to a depth where the pressure is 7.4 or 4.7 atmospheres and the temperature is 15 degrees C, what will its volume be? We're going to assume that any changes in pressure caused by the skin of the balloon are negligible, which is, don't worry too much about that. It's just the balloon becomes less elastic as it gets colder, so it doesn't stretch as easily. All right, so we have our three gas laws, P1, V1, P2, V2, V1 over T1 equals V2 over T2, and the combined so again, just because I think that one of the trickier things with these gas law problems is which equation do you use, because there are so many. In this case, we do have volume, pressure, and temperature, and both volume and temperature change. Sorry, volume and pressure change. Sorry, pressure and temperature change. So we go from 1.1 atmospheres to 4.7 atmospheres, and then 30 degrees C to 15 degrees C. So with two variables changing, we have to use the combined gas law. So if we have the combined gas law, we're going to have P1, V1, T1, and P2, V2, and T2. So what's our P1?
1.1 atm.
1.1 atmospheres. And our volume one? 3.7 liters, yep. And then our temperature? Yeah, 30 degrees C. Pressure 2?
4.7 atmospheres.
It's not unknown. Yeah, this one's not unknown. It's our 4.7 atmospheres, because we have that here. The question is, what will the volume be? So volume is going to be our unknown. And then our T2 will be 15 degrees C. Now, what are the restrictions on units for gas law problems? What units do we have to be using?
Kelvin?
Kelvin, yeah. Kelvin is the only one that we're really restricted to. The other units just have to be the same on both sides. So here we have atmospheres and atmospheres for P1 and P2. We have volume in liters, so we'll solve for volume in liters. And then these guys need to be converted into Kelvin. So to do that, we'll add 273.15. So this is going to be 303.15. And 288.15. Okay, so now we can really just plug these numbers in for our equation. And again, if you want to rearrange your variables beforehand, you can do that. Actually, maybe it would be easier. It's going to take up less space if I rearrange the variables beforehand. Okay, so we need to multiply by the same thing on both sides. And we're going to multiply by the inverse of the things that we want to remove. So if we want to find volume, let me highlight that. Volume is what we're looking for, so we want that to stay there. So we're going to multiply by T2 over P2 on both sides. So we'll get T2 not equals T2 P1 V1 over P2 T1 equals V2. And now we can just plug these numbers in. 288.15 times 1.1. Oh, let me put units. Times V1, which is 3.7 liters. And P2 is 4.7 atmospheres times T1, which is 303.15 Kelvin. And so when we look at our units, that didn't help. When we look at these units, we see that we have Kelvin divided by Kelvin, atmospheres divided by atmospheres. So those units will cancel, and we'll just be left with units of liters, which is what we want for V2. So this will be 288.15 times 1.1 times 3.7 divided by 4.7 divided by 303.15. So our new volume is going to be 0.82 liters. Cool. And again, you can kind of do a logic check. And based on what we know about Boyle's law and Charles' law, right, we can determine what the relationship between pressure and volume should be. So if our pressure goes from 1.1 atmospheres to 4.7 atmospheres, that's an inverse relationship. So as pressure goes up, volume goes down. So that makes sense because our volume goes from 3.7 to 0.82. And then our temperature goes from 303.15 to 288.15. And according to Charles' law, as temperature goes down, volume should go down because it's inversely, or it's a directly proportional relationship. So both of these things say our volume should be smaller. So it's actually going to be a lot smaller than our starting volume. So it makes sense. Okay. One last gas law that we have here is Avogadro's law, which is the relationship between volume and moles. So if we add more air, more gas to a container, and keep the temperature and the pressure the same, the volume of the container has to get larger. Right, so as we add more on this x-axis, we're adding more number of moles. Our volume has to increase to keep temperature and pressure the same. So volume of a gas sample increases linearly with the number of moles in the sample. So this is another directly proportional relationship. And we can do this one on the simulation too. Oh yeah, perfect. Let me see here. Yeah, so we set a temperature. Right, cool. Oh. Let's heat this up a little bit. Okay. So as I add more particles to this box, I'm clicking down here. Actually, I'll use the bike pump. There's this bike pump here. And so I can pick this up and put it down, and that'll pump more air into our box. So as we pump air to the box, the volume gets larger, but our pressure stays the same. Our temperature, did our temperature change? Temperature probably stays the same. Yeah, temperature stays the same as well. And then I can remove particles from the box as well. So if we think about this in terms of kinetic molecular theory, if we've got these particles in here, you can also think of this like a balloon. When you blow up that balloon, the pressure inside the balloon wants to be equal to the pressure outside the balloon. So as you add more particles to it, you're adding more collisions inside the box. See how well this works out for this. Let's do just 5. So 5 picoseconds, it's 103 collisions, 106 collisions, 105 collisions. And that's to maintain 14.4 atmospheres. And actually, if I held the size of the box constant, then our number of collisions would go up and our pressure would go up. But if I add more particles, we should get roughly the same number of collisions because the box has gotten larger to accommodate those extra collisions while keeping the pressure the same. Wait, this one. Come back. Oh, it did switch. Wait. Oh, that's cool. Didn't know it would work like that. I'll post the link for the simulation too if you want to go and just play with it and try and get a better handle for these gas laws. Okay, so Avogadro's number, though, practically speaking, is this equation where increasing the number of moles or increasing the volume, increasing volume, you have to increase the number of moles. Increasing the number of moles increases the volume. So I think the best example is blowing into a balloon because you're adding more air to the balloon, so it gets bigger. Because there are more particles inside to collide with the walls of the balloon. All right, so for Boyle's law, P1 V1 equals P2 V2. Charles' law is V1 over T1 equals V2 over T2. The combined gas law, PV over T. And now we have Avogadro's law, which was it volume on top? Volume on top. Oh, good. I can show you. There's a trick that Mrs. Cornell actually texted me after class yesterday that I can show you guys here. So again, we've got these 4 different equations now. And don't be too freaked out by that. Just look at the types of units that you're given in the question. So we've got 4.8 liters of helium gas contains 0.22 moles of helium. How many additional moles of helium must be added to the sample to obtain a volume of 6.4 liters? Right, so liters is always going to be volume. Moles is always going to be the number of particles. Millimeters of mercury, torr, pascals, and atmospheres are all different units of pressure, but they're always pressure. So here we know we're not going to use any of these because none of them have moles in them. So Avogadro's law, we have V1, N1, V2, N2. So we have a 4.8 liter sample of helium gas, contains 0.22 moles of helium. How many additional moles of helium must be added to a sample to obtain a volume of 6.4 liters? And then N is our unknown. So when I showed this to you before, right, we did It's a similar thing with Charles' law. Things are a little bit more complicated if you're solving for one of these numbers in the denominator. So in this case, moles. What you can actually do is just flip the whole equation. Because this is just the proportion between these two numbers, we can write this as n1 over v1 equals n2 over v2. So as long as on both sides of the equation we have n1 on top, n2 on top, v1 on bottom, v2 on the bottom, we can just flip this equation upside down and make it a little bit easier to solve. Because now instead of solving for n2 in the denominator, having to do a bunch of algebra to flip things around, we can do a little less algebra to solve for n2 on top. And the same thing works for Charles' law. So if you had to solve for temperature, you can flip it, make that a little easier. And for the combined gas law, you can flip the P1 V1 over T1. So it's T1 over P1 V1 equals T2 over P2 V2 if you're solving for temperature. Because then if we want to rearrange this before we start the equation, we'll just multiply by V2 on both sides. Wait, I did this backwards. So then we get V2 N1 over V1 equals N2. And then it's just plug and chug. So V2 is 6.4 liters times N1, which was 0.22 moles, over our V1, which is 4.8 liters. And again, here we've got liters divided by liters, so those units will cancel, giving us the units we want, which are units of moles. So 6.4 times 0.22 divided by 4.8. 0.29 moles equals V2. So does that answer make sense? So we had a volume of 4.8 liters, and we want to make the balloon bigger. So should moles be going up or down? Those? Up, yeah. Sorry, N2. Thank you. Yeah, so our moles should go up. Yeah.
So the N stands for the number of moles, correct? So
Yes.
that's why it's the letter N as the variable?
Number of moles, yeah.
Okay. Or number of particles, right?
Number of particles. It is, yeah. I don't know exactly if it's N because of number of particles, but if that helps you remember it, yes. That's a good way to remember it.
Okay.
Yeah. What was that? T is temperature. Yeah, T is temperature, V is volume, P is pressure. Yeah. Okay, so another question here. So a chemical reaction occurring in a cylinder equipped with a movable piston produces 0.58 moles of a gaseous product. If the cylinder contained 0.11 moles of gas before the reaction and had an initial volume of 2.1 liters, what was its volume after the reaction? So again, we've only been given units of moles and liters here. So we're going to be using Avogadro's law. But this question is worded in a way that makes it harder to tell which one's V1 and N1 versus V2 and N2. I will say it only matters if you get the sets of conditions right. So But let's get these down first for this one, and then I'll explain what I mean by that. So what's our V1? Yeah, 2.1. Because it says initial volume. So what's N1?
0.11.
Mm-hmm. 0.11 moles. So then that really only leaves one number. So our V2 will be what we're looking for. And our N2 is 0.58 moles. So what I mean when I say it only matters which one's, V1 and N1 versus V2 and N2 is if it's the same set, meaning if it's the matching conditions. So our initial volume was 2.1 liters, and we had that volume with 0.11 moles of the gas. But this could be V2 and N2, and these two could be V1 and N1, and you're still solving for the one missing variable. It's just easier to think about V1 and N1 as the initial conditions, V2 and N2 as the ending conditions. Okay, so we're solving for V2. So V1 over N1, V2 over N2. So should we flip this equation? Put N on top? No. We want to solve for V2, so this is already the easier way to solve it. And now we can multiply by, maybe I was doing it. Was I doing it the other way? Doing it like this, huh? So we're going to multiply both sides by N2. And you can think of this if you want as N2 over 1. But multiply by the same thing on this side as well. So we get N2 V1 over N1 equals V2. And then we just plug our numbers in. So 0.58 moles times V1, which is 2.1 liters, over N1, which is 0.11 moles. So moles will cancel. We'll be left with units of liters. So 0.58 times 2.1 divided by 0.11. I think, did you guys get 11? Okay. I hit something wrong on my calculator, tried to undo it, and I apparently did it correctly. So 11 liters would be our V2, so after the reaction. Now, does that answer make sense? Based on how the number of moles changed. So we have an increase or decrease in number of moles.
Decrease, right? No.
Our initial was 0.11, went to 0.58, so it increased. Yeah, so we had an increase in number of moles. So then Avogadro's law is a directly proportional relationship. So yeah, our volume should have increased. And actually, you can look at this and see that number of moles went from 0.11 to 0.58, which is roughly 5 times bigger. And our volume from 2.1 to 11 is also about 5 times bigger. And that'll actually always be the case. They'll increase by the same proportion. All right, now we can bring it all together. So Boyle's law, Charles' law, and Avogadro's law really can only predict a change. So we have to know what the conditions were before. So like this problem here, right? We had this volume, this number of moles, and we went to a new number of moles. So we can use one of these gas laws, Avogadro's law, to predict what the new volume would be. But we can't use any of these individual laws to figure out an unknown for any set of conditions. So for those of you who did the lab on Monday, used PV equals nRT to solve for the number of moles of hydrogen that you produced, based on the volume of hydrogen that you produced. So the ideal gas law lets us do that, and it uses this fancy constant, 0.0821, and then the units of this are extremely important. So for pressure, we're always going to be using atmospheres. For volume, we're always going to use liters. For number of moles, we use moles. And temperature always has to be in Kelvin. So with the other gas laws, didn't really matter. Aside from Kelvin, temperature always has to be in Kelvin. When you're using the ideal gas law, PV equals nRT, I guess I could also say, some people just pronounce it as PivNert. Our units always have to be the same as R. So in this case, liters, atmosphere is mole Kelvin, because if you change one of these, then R changes and it's something else. So if you change atmospheres to millimeters of mercury, is the only one I know off the top of my head, it's R equals 62 instead of 0.0821. I would recommend spending some time with this table and trying to understand it, because I think understanding it can give you a better grasp of sort of the core of these things. It's a little bit hard to explain. But for each of these simple gas laws that we had, we didn't talk about Gay-Lussac's law, but it's a relationship between pressure and temperature. We're holding other things constant. You have a question? No. No. Sorry, I lost my train of thought. We're holding things constant. So if we take our equation, PV equals nRT, we can rearrange this and get basically divide by RT on both sides, or sorry, not RT, NT on both sides, so that PV over NT. This PV equals NT, PV over NT, if we have that as an initial set of conditions, so we call this P1, V1, N1, T1, and then we have a new set of conditions, P2, V2, N2, and T2, you can actually derive all of these simple gas laws from this. So this is basically assuming that nothing is held constant. So if we have a change in pressure, that's going to affect volume, number of moles, and the temperature. The simple gas laws, so let's say we want to do Boyle's law. So we hold N and T constant. So if N and T are the same on both sides of the equation, they'll cancel out. So if N and T are constant, we can cancel them out of this equation, and that just leaves us with P1 V1 equals P2 V2, which is Boyle's law. If we want Charles' law, then we're holding constant number of moles, N and P. So I'll write this again. PV over NT equals, those are all 1, these are all 2. So we're holding N and P constant. That means on both sides of the equation, N and P will be this exact same thing. So P will cancel, N will cancel, and we're left with V1 over T1 equals V2 over T2. So you can derive or get to any of the individual gas laws from this P1 V1 over N1 T1. And you can actually even use this for the other questions that we did. Let's go back to this Avogadro's law problem. if we have P1, V1 over N1, T1, so let's look at our variables here. Well, I guess in this problem it doesn't specifically say that the other things are being held constant, but they are. So the only things that change are volume and number of moles, which means that pressure is going to be constant and temperature is going to be constant. So we can take those out of the equation and just use the variables that are left behind, which are V1 over N1 equals V2 over N2. So the ideal gas law is pretty powerful. So that use of the ideal gas law I just showed you is for where we have things that are changing. Here we just have a set of conditions. So we're only given, let's read through the problem, calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. So we've only been given one of each parameter. Right, we've got 1 mole, 1 atmosphere, 1 Kelvin. There's not a change happening. So simple gas laws you use for changes. The ideal gas law in this form we'll use just for a static set of conditions. Here, what's the volume? So we can write this out a similar way though, right? P, V, N, I'll write out R and then T. So our pressure is going to be 1.37 atmospheres. Our volume is what we're looking for, 0.845 moles. R is always going to be 0.0821. And the units are atmospheres, liters per mole Kelvin. And our temperature is 315 Kelvin. And actually, you can use just the units of R to figure out PV equals nRT. Because when you have PV over NT equals R, this is atmospheres, liters per mole Kelvin. Okay, so we can just plug these into our equation then. We have 1.37 atmospheres times V equals 0.845 moles times 0.0821 atmosphere liter per mole Kelvin times 315 Kelvin. So divide both sides, or multiply by the inverse. So 1 over 1.37 atmospheres to get V by itself. I'm not expecting you to write out like all of what I'm writing out here. Just trying to provide some algebra examples on these problems. So then we're going to just take our 8.45 times 0.0821 times 315 and then divide by 100 or 1.37 atmospheres. So then our volume is 16.0 liters. I do want to point out here, though, that if you look at the units of R, here we have moles times what is 1 over moles, Kelvin times 1 over Kelvin, and then atmospheres divided by atmospheres, so that the only units we end up with are liters, which is what we're looking for. Yeah.
Would it be 16.1 or just 16.0?
I got 15.95,
Oh, yeah, okay.
so 16.0. Because you round the, well, 3 sig figs, you round the 5 up. Wait, sorry. 3 sig figs, so you round the 9 up because the next digit's a 5. Yeah. All right, so again, another ideal gas law problem. We have 8.5 liters. An 8.5 liter tire is filled with 0.55 moles of gas at a temperature of 306 Kelvin. What is the pressure of the gas in the tire? So again, our equation is PV. So we got P, V, N, R, and T. So pressure is what we're looking for. Of 8.5 liters, 0.55 moles. R is always the same, 0.0821 atmosphere liter per mole Kelvin. And our temperature is going to be 306 Kelvin. So if we rearrange this equation to get pressure by itself, we'll have P equals nRT over V. And then we can just plug our numbers in. Temperature is 306. Divided by a volume of 8.5 liters. That'll give us pressure. Oh. That makes sense. Divided by 8.5. So our pressure equals 1 point, looks like we have 2 sig figs, so 1.6 atmospheres. So again, the trickiest thing about these problems is not necessarily the math. It can be figuring out which equation to use. But this PV equals nRT is always going to be when we have one of each of those. And then for the other equations, you're always going to have a change. So you'll have more than one pressure, more than one volume, more than one number of moles, or pressure, volume, moles, or temperature. Aha, of course. Okay, so how much volume does 0.556 moles of gas occupy when its pressure is 715 millimeters of mercury and its temperature is 58 degrees C? So we're still using PV equals nRT. PV V N R T. What is our pressure?
715 mercury. Yeah.
Mm-hmm. And our volume?
We don't have it.
Right. We're looking for volume. Number of moles?
0.556 moles.
Yep. What's R?
0.0821.
What are the units?
L-A-T-M. Kelvin.
I think you already know where I'm going, but, and then 58 degrees C, temperature. Yeah, so remembering these units of R is important because we do need to convert 715 millimeters of mercury into atmospheres. So that is going to be, we have 1 atmosphere equals 760 millimeters of mercury. So we'll take our 715 and divide by 760. So that'll give us our atmospheres. So 0.940. Oops. 89474. Because we don't want to round anything yet. And then for temperature, it also needs to be in Kelvin. It's 273.15. Add 273.15. 58. This is 331.51 for 15, sorry, Kelvin. So again, I'm going to rearrange this so that we get volume by itself. So V equals nRT over P. So our volume is going to be 0.556 moles times 0.0821 atmosphere liter per mole Kelvin times our temperature, which is 331.15, divided by our pressure, which is 0.940789474 atmospheres. So 0.556 times 0.0821 times 331.15 divided by a big number. Well, not a big number, but a long number. V equals 16.1 liters. Yes? 2 questions. Go ahead. Go ahead.
So, how come we added, like, 273.15 to the temperature, and why did we divide 760 and then H to the pressure?
Yeah, so adding 273 to degree C is converting it from degree C to Kelvin, which we need to do because our R is in, or has units of Kelvin in it. So it doesn't have degree C, but it has Kelvin, so we need to use Kelvin there. Then this is also converting from millimeters of mercury to atmospheres, again, because R has atmospheres in it. So I can write this out a little more clearly. 715 millimeters of mercury. So we multiply by 1 atmosphere divided by 760, because that's the conversion factor there. Yeah.
I have a question. So we would use a 3 sig figs based on like the 0.556 moles, right? Because that has 3 sig figs and we're using the least amount of sig figs.
Correct.
Okay.
Because it's all multiplication division.
Yes. Okay.
Yeah. Are there any other questions?
So in order to figure out how many sig figs we have, it's always the n?
Not always n. It'll be the smallest number of sig figs for a multiplication division. Yeah. In this case, yeah, I mean, I'll probably give you degree C and something more. But because we did this plus this, it's not the smallest number of sig figs, but the fewest number of decimal places. So we keep 3 there. Yeah. Any other questions? Alrighty. So if we can calculate the number of moles of gas, we can also calculate the molar mass of a gas, as long as we have the mass, which you can do. So you can take like actually did this experiment in my undergrad, and these scars are from that experiment because our professor had these glass bulbs and they had like a valve on them. And so you could turn this valve and it would let gas in and out. And then we hooked that up to a vacuum and it would suck all the air out, and then we would fill it with pressurized oxygen, suck it all out, fill it with pressurized oxygen. And then if you knew the mass of this glass vessel while it was empty, you could figure out the mass of the oxygen inside of there, or the mass of the nitrogen inside of there. We did a few different ones. But that thing exploded while I was holding it in my hand, and then shot shards of glass into my left arm. It's like this scar, this one, and this one. That's why you always wear lab goggles. Yeah, it was like a shotgun going off in the room. So you can figure out the mass of the gas pretty easily if you have good equipment. Not too hard to do. Figuring out the number of moles of gas is more difficult, but with ideal gas law, we could do that if we have the volume of the container, we have the temperature of the container, and the pressure inside the container. But why is this written like this? Okay, so I'm going to do some conversions here for you because time. So if we have a sample of gas with a mass of 38.8 milligrams, its volume is 224 milliliters at a temperature of 55 degrees C and a pressure of 886 torr. Find the molar mass of the gas. So this is going to be 0.0388 grams. We'll need that later. It's going to be 0.224 liters. This is going to be 8086 divided by 760. So torr in millimeters of mercury are the same. So we can take 886 torr divided by 760. That'll give us 1.165, again, keeping those numbers. And then this is 55. This is 328.15 Kelvin. So we can plug most of these numbers in, again, to PV equals nRT. Actually, I think we're going to do the molar, not the same molar mass of a gas experiment that I did, but a different one. One that involves not so much pressure or opportunity for explosion. So we can rearrange this into PV over RT equals N. And then our pressure will be this 1.165 atmospheres times the volume of 0.224 liters divided by R, so 0.0821, times our temperature, 328.15 Kelvin. So 1.165 times 0.224 divided by 0.0821 divided by, yep, that number. Oh wait, no. I did it wrong. It's this times 0.224. So this is 0.00969 moles of gas. So how can we find the molar mass of the gas? What was it? Yeah, it's the ratio of moles to grams. Specifically, we put grams on top, grams per mole. So we can take this 0.0388 grams and divide by our number of moles. So the molar mass of this gas is 0.0388 divided by 0.00969 ... And we actually get that this is 4.00 grams per mole. So what gas do you think this is?
Helium?
Wait, yes, helium. So it could be helium, could be something else. Yeah. Helium. I was thinking for some reason I was checking in my mind, like, could it be one of the Brinkelhoff, right? Because hydrogen would be a molar mass of not 1, but 2, because it's H2. But yeah, so most likely that this gas in this vessel is helium. Oh, yeah.
I just had a quick question. When we got the 4.00 grams per mole, did we use mole ratio for that? The grams over the 0.00969.
What do you mean by molar ratio?
Well, because I know we have to convert from, was it moles to grams, right? Molar mass?
So yeah, so molar mass
Okay.
is grams per mole.
Grams per mole. Okay.
So if we take grams and divide by mole, that will give us grams per mole.
Got it.
Yeah. Do you have another question? Is there another one? No? Okay. I thought I saw another hand. I'm like really frustrated that these have so many other conversions in them. So a sample of gas has a mass of 827 milligrams. Its volume is 0.270 liters at a temperature of 88 degrees C and a pressure of 976 millimeters of mercury. Find its molar mass. So we got our PV equals nRT. So we have PV over RT. Now pressure, 976, that's millimeters of mercury. It's not great for our R value. So 976 divided by 760 equals 1.28. Our volume, 0.270 liters. N is what we're looking for. Temperature, right? So our temperature is 88 degrees C. 88 plus 273.15. It's going to be 300 and 361.15 Kelvin. So again, just making sure that everything is in the correct units. So when we plug these in, the units will all cancel out properly. So 1.28 atmospheres times 0.270 liters divided by 0.0821 times 361.15 Kelvin. So we're going to have 0.0117 moles of gas. So if we take our mass here of 827 milligrams, for molar mass is in grams per liter, or grams per mole, grams per liter. So we can take this decimal place and move it over 1, 2, 3 spots. And that'll give us 0.827 grams divided by 0.0117 moles. Gives us a mass of 70.7 grams per mole. .7. So to find the molar mass of a gas, you have to be given the mass of the gas, and then you just find the number of moles using PV equals nRT. So really it's just kind of hiding the fact that you're looking for N behind the fact that you're actually going to carry that on to do one more calculation. The other kind of question that you could get, and maybe it's going to be the next one, no. The other kind of question you could get on something like this is that you have some mass of the gas, and then I'd have to tell you what the gas is, and then ask you, what's the volume if the pressure is this and the temperature is this. Then you'd have to calculate from mass of the gas to moles of gas. Plug that in with the rest of the stuff into PV equals nRT and find volume. Do we? Okay, so for all of this, we've been talking about ideal gases, which is not all gases. So ideal gas conditions, you have high temperature and low pressure. So the particles are moving really fast, relatively speaking, and there's not many particles around. Because as you do start to pack more particles in, actually we can go back over to this simulation. Let me constrain nothing. We can just pack a bunch of particles in here. See our pressure goes way up. In a real world scenario, if you had this many particles all bumping around inside of there, some of them would start to condense. So they would start to be pushed so close to each other that our ideal gas conditions fall apart. Because remember, our ideal gases are far apart from each other, and they don't interact with each other aside from when they collide, they bounce off. But when you force them all into a space that's too small, they do start to stick together. And you've seen this probably if you boiled water and you put a glass lid on top. Those water molecules are then sticking to the glass and then sticking to each other and then condensing. This is going to be really distracting if I don't clear it. So those are your non-ideal gas conditions. As we start to get these things closer and closer together, the interactions between those particles become significant, and ideal gas laws kind of fall apart. There are corrections that you can make to the ideal gas law so that it still works, but we're not going to go into that. Just know that what we're doing is ideal gas laws won't apply to all gases. So really the last concept that's in here, and we won't finish it today, but what happens when you have mixtures of gases? Up till now, we've been kind of talking about them as if they're all the same and all equal. But the amount of each individual component in a gas mixture is called the partial pressure. Because if you had 50% oxygen, 50% nitrogen, each of those particles would be contributing half of the pressure to any container. Because remember, pressure is those molecules actually colliding with the sides. So if half the molecules colliding with the sides of the container are oxygen, half are nitrogen, then the pressure of each of those is 50-50. And that's what the partial pressure of any component is that component's, what do I want to underline here? Is that component's, so partial pressure of a component is the component's fractional composition times the total pressure. So what that means is, like I was saying, so if our total pressure, let's use millimeters of mercury for this. So let's say our total pressure is atmospheric pressure, 760 millimeters of mercury. And like I was saying with my example, fractional composition of something, let's say it's 50%. So 0.50, right? That's half. So the partial pressure of, let's just say this is oxygen, it's going to be 760 times 0.5. So 380 millimeters of mercury. 380 millimeters of mercury of pressure is coming from oxygen, and the other 50% is coming from the other gases. We'll see if we get to it here. So for air in our atmosphere, these are the rough compositions. 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, and a few other gases. So 78% of the total pressure in the air is just coming from nitrogen molecules bumping into you. Then 21% from oxygen. So the optimist sees the glass as half full, pessimist sees the glass as half empty. The chemist is that the glass is full. It's just 50% water, 39% nitrogen, 10.5% oxygen, and so on. So it's full, it's just not all water. I don't want to go through these examples quite yet. I mostly just wanted to mention that we'll come back, we'll do all of these, but this is relevant for the lab that we did this week, or you will do this week. If you have a liquid, there's always some amount of pressure above that liquid in a container that's due to the liquid turning into a gas. And it's related to the temperature. So in the experiment we'll do today, the water temperature, which we just used as the room temperature, is important because that determines how much of the pressure in your vessel containing your hydrogen, how much of that's coming from just water. So you need to subtract that out, otherwise it's error. Okay. Take this back here. Yeah, that's it for today.